So we've kind of gone relatively low tech on this one, and there's definitely ways to do it with a higher tech setup. But effectively what we're going to do, this is force on a magnet. So we've got, initially we'll go with a bar magnet and a spring balance. And what you do ideally is measure distances from the magnet and forces that are acting. So unfortunately, it's really quite challenging with a spring balance because it tends to be either grabbed or not grabbed. So we'll demonstrate that, and what we're going to do is record the force at which it lets go. Our spring balance is denominated in grams on the left and in newtons on the right, so it makes our life easier. We can go straight to newtons. And I'm just going to pull them apart slowly and make a note of the force, the number of newtons at which the magnet lets go, at which the spring balance and the magnet part company. So it's up to 300 or 3 newtons. It was just a little over, and I was talking rather than watching, so I'll have to go again. So it was a fraction over 3 newtons, and now I've calibrated it. Like as we do with all of our experiments, we'll do multiple trials, so that will help with that. And I don't think I would include that first one because it was a mistake. It was a not accurate one, but I will do another 5 or so that I'll actually record in the data. But I know now where to look for it. I know that it's just above 3 newtons somewhere. So that's 3.46, and it was getting towards 3.8. It's quite tricky. We might actually use some slow-mo video to get that maximum measurement on the scale just as the magnet lets go. Now that is, we're not using anything on the end of the spring balance, it's just its own magnetic or metallic hook, and we're just using an ordinary bar magnet. Now we can step it up a little bit and use a neodymium magnet, and we're going to start with a tiny one. Now these guys are quite tough in terms of health and safety. You want to be very, very careful, even though this one is really tiny. It's half the diameter of a 5-cent piece, something like that. It's quite tiny, but it's quite a potent magnet. These neodymium magnets will trap your fingertips and do serious damage to them, or they can fly together with another one or any other magnet or any other piece of metal and fire off a small shard at great speed. So handle with considerable care. So, and eye protection. So I'm going to hook the balance to it and do the same procedure. We'll go up 2 Newton, 3 Newton, 3.8. So it's definitely more powerful than our bar magnet. Oh, and it went at about 4.2 as my fingertips were about to go as well. So we can do the same thing. I'm trying to pinch that and test it. I think it went at around about 4.2, but again, a lot of your phones will have slow motion capacity, which is really helpful for this kind of thing. It's one of the ways that we use ICTs in the lab, is to use the thing that every student has pretty much to actually capture something that's really hard to capture with the naked eye. So that's our small neodymium magnet. Now we'll try a big one, and I'm being even extra careful with this guy because it is potent enough that probably the fact that there's metal under the table is likely to influence it, and it certainly will grab any of our other magnets, and I've moved everything well clear of that guy. So I'll put that in. Now we're going to find, I think, that if we hook that balance to it, we will go to 3.8 where the bar magnet went. We'll go to 4.2 where the small neodymium went. We'll go to 5, and now we're off scale. This spring balance isn't strong enough to actually measure this force, so we need to upgrade to its bigger brother. So this one goes to 20 Newton rather than 5 Newton. Same kind of scale, same manufacturer, etc., but just a more potent balance. So let's see what the force at which it lets go is for this one. So we've gone above 5 Newton, only a little bit. So maybe we only just missed it with, as you can see, they will grab if they get a chance. Maybe the little balance almost got there. So we go 4, 5, 5.5, just under 6. I think though that if I rotate it, we might get a higher reading. Let's test. Maybe not. Let's check. So what you might need to do is have a little diagram as well as a description in your lab book that says when we held it this way, it had this force. When we held it that way, it had that force. So now it's above 6. It's around about 6. It's a little bit higher than it was before. And we might do that same slow-mo trick to try and get an accurate measurement in newtons of the force at which the magnet lets go. Now, as I said, what we would probably ideally do is set it up so that you can see how much fun and how much of a hassle these things are. We would set it up so that there was a 2 millimetre gap between the two and measure the force, and a 3 millimetre gap and a 4 millimetre gap. It's really quite a tricky setup, and you would want lots more clamps than my fingertips and so on. But you could actually set that up so that you're measuring how the force on a magnet changes with distance over time, rather than just as we are measuring that sort of brake force, the force that's exerted at the point where it can be overcome by the force on the spring balance.